I'm done.
Okay, Rani. From here, we'll continue in the next class. Okay.
Ma'am, can you show the final equation once?
This is just the final equation.
Yes, ma'am.
Okay. Okay. Fine, Rani. You can leave. Okay.
Okay.
Yes, Halima, am I audible to you? See, this part was done. This was completed. Okay, we were on the Faraday's experiment. This has to be started. See, basically, what is Faraday's experiment? Let me tell you. He was just checking whether the magnetic field can produce any sort of deflection or not, any sort of current or not. So he took a moving coil galvanometer. Now, if you remember, we discussed that the galvanometer, this shows a deflection when the current is present in your circuit. So if the current is present in your circuit, we'll say the deflection is there. That is, the current is present. So what did he do? He took a bar magnet, not some, and he brought it closer. As soon as he brought closer, he could see deflection. It means current was produced. Magnetic field led to magnetic field lines, led to magnetic flux. Similarly, in experiment 2, what did he do was he took the same coil, okay, but this time instead of moving the coil, let me make the coil. This is the galvanometer. This is the bar magnet. Instead of moving the bar magnet, he moved with the coil directly. But same result because as soon as it got closer, it had magnetic field lines. Magnetic field lines would have produced alternating the direct current. That was the whole experiment point that yes, current was being produced. Last one is you take soft iron rod, you wrap it with wires and connect galvanometer in one of these. And finally, the free end is connected to the battery or rheostat. So this we'll study in alternating current. Here you don't have to do this. So basically, what's the whole conclusion by this Faraday's experiment? Whenever the magnetic flux was changing, we could see that induced current and induced EMFs were produced. Right? Induced current and induced EMFs were produced. The higher the rate of magnetic flux, the greater is the induced current or induced EMF. So there are a few laws that you have to remember for the Faraday's law. Whenever magnetic flux linked with the circuit changes, EMF is induced, and this EMF is directly proportional to the magnetic flux. Let's say phi I is equal to initial magnetic flux, phi F is equal to the final magnetic flux. Okay. Now see, you can directly say that EMF is directly proportional to rate of change of magnetic flux. Directly you can say this. E is equal to minus d phi over dt. This is the complete value. Just a minute. Okay. So see, E is equal to minus d phi over dt becomes our formula. Where E is the EMF, d phi over dt, this is the rate of change of flux. Rate of change of flux. Now, what is this negative sign? We will be discussing this negative sign in the Lenz law. Now, see if R is the resistance of the circuit. E is equal to IR. Now, E is equal to d phi over dt into IR. So, current can be written as 1 by R into d phi over dt. This is the EMF. Okay, correct. Then let's say you have a charge small q. So what you can do, look, if I is equal to 1 by R and all, so let's replace this I with dq over dt. So this will be 1 by R d phi over dt. Dt will be cancelled. So q you can say is d phi over R. So these are various formula that you have to understand in a sequence. After that, let's practice questions because here two questions are there. This magnetic flux topic will be over. Write it first. Now see, coming to the Faraday's law. So, okay, this part you have not written, no? First you complete it. Then we'll discuss the numericals. This part is left, no? Just till here you have written.
Can you scroll up? Done, ma'am. Done, ma'am.
See, I hope you've written till here. Now let's see the question. This is a 10 ohm resistance coil of 1000 turns. Number of turns 1000. Resistance 10. And at a time, flux is means initial flux is 5.5 into 10 to the power minus 4 vapors. It passes through it, it falls to final flux is 0.5 into 10 to the power minus 4. Okay, the rate of change of flux when you're calculating the flux here, a time is also given to us as 0.1 seconds. Then says we have to calculate the EMF generated and what's the value of the charge. Class. For EMF, the formula which is simple, minus d phi over dt. For n number of turns, it will be minus n d phi over dt. Look class, n is 1000, change of flux, final flux is 0.5 into 10 to the power minus 4. Initial flux is 5.5 into 10 to the power minus 4 divided by 0.1. This will be how much class? See, minus will become plus 10 to the power 3 into 5 into 10 to the power minus 4 into 10 to the power minus 1. No, 10 to the power. That is simply 5. First, tell me, is the EMF part clear, class? How is this calculated? Is it fine?
Yes, sir.
Okay. This charge also. So charge, we have discussed it as flux change by the resistance. Flux change is minus 5 into 10 to the power minus 4. Resistance is given as 10. So that will be minus 5 into 10 to the power minus 5 volt. This is one question. This question is from your NCRT. I'll discuss this. That will complete the first topic and then I'll start with the next one. Okay, write down this question first.
Ma'am,
Yes, done. Halima, what are you saying? Completed?
no, ma'am, the negative sign right at the last step, end of the answer.
Mm-hmm.
It
Yes,
is
yes.
due to the lens law or like,
This is due to the flux, no? We are subtracting lesser minus greater because flux is
no, ma'am,
decreasing.
it will be positive, right? Like, because there's minus 1,000 over there. And we'll get -5.
Okay, you're saying because of the lens, right? See, that is with regard to the direction. Right now, we are talking about the sign of the charge. Okay, so sign of the charge is negative, but see, when you will combine it with this, E is equal to this lens law, that will tell the direction. Now, see, charge doesn't need the direction. You can put it minus also, you can put it plus also, but here then you'll have to show that this is because of the lens law. Okay, E is equal to minus d phi over dt is actually the Lenz law. So you can avoid it in this case also because this will just tell you the value for the charge. Okay, you can put it as plus also. That will be just understood that that is due to the sign because charge is a scalar quantity and it doesn't need so much attention on the direction, and negative sign is because of the charge. Otherwise, this minus that I have written here, this is due to the flux one. Okay.
Okay.
Okay, C class. This says a coil of cross-sectional area A lies in a uniform magnetic field B with its plane perpendicular to the field. Now see, coil makes an angle 0 degree with the field. It says that the coil at a uniform rate means it is at a uniform rate. This coil is rotating. Okay, to complete one rotation, or in fact, this is saying in complete time period of t. It says find the average induced EMF. Look, class. Coil of cross-sectional area A is there. It is lying in a magnetic field B, which is perpendicular to the field. Area vector in magnetic field will make an angle of 0 degree. Now you'll have to see the other things. It says in this position, normal to the coil makes an angle of 0 degree with the field. Okay? Because perpendicular will be 0 degree with the field. Magnetic field is also perpendicular. Normal is already perpendicular. This says the coil rotates at a uniform rate to complete one rotation in time capital T. Means if I draw it like this, the complete time taken from going from 0 to 90, 90 to 180, 180 to 270, 272 back to 360. This complete time is capital T. This first part says 0 to 90 degree. Can any one of you tell me what will be the time period for this one? Total time is given. Tell me 0 to 90 degree. Total
T/4.
is T. Yes? How much?
T/4.
Yes, very good, Vishri. See, the time that you're going to take, no, that will be T by 4. Now, see, we are going to calculate the flux. Initial flux will be B dot A, that is BA cos theta. Initial angle is 0 degree. That will be equal to plus BA. Let's calculate the final flux. Final will be at 90 degree. So B dot A will be BA cos 90 degree, which will be 0. Now let's apply the Lenz law. Sorry, the Faraday's law. E will be equal to minus d phi over dt class. Minus of, now final flux is 0 minus initial flux is BA divided by time is T by 4. That is BA by T by 4, which is equal to 4BA by T. Clear this part?
Yes, ma'am.
Okay. Second is 90 to 180 degree. In this also it will be T by 4 only. But if I change the values, the answers will be different class. Like if I make it 0 to 180 degree, it will be T by 2. 0 to 270 degree, 3T by 4. 90 degree to 270 degree, T by 2. Like this, the way we have solved fractions, similarly you have to solve this. To solve this. 90 degree to 180 degree. Uh, For 90 degree to 180 degree, what you do here, time is still t by 4. Okay, this is still t by 4. Now, initial flux when we are calculating, it will be BA, that is B, sorry, B dot A, that is BA. Initial angle is what? 90 degree. 90 to 180 degree. So from 90 to 180 degree, this will be 90. So cos 90 degree, which is equal to 0. Final flux will be again B dot A, that is BA cos 180 degree, which is equal to -1. Coincidentally, the values are same in this, so answer would probably be the same because values are same. No, -1, minus not 1, sorry, minus of BA. So minus d phi over dt class, minus of final is minus BA minus 0. Again, it's coming the same, but see, this is not a fixed value for BA by T. For every answer, it could be different. This is just a coincidence because this is also -1, this is also T by 4, that's fine. But have you understood this question, class? Huh?
Yes, ma'am.
Yes, ma'am.
Okay, there's a question in your NCRT similar to this. So please attempt that also. Write it. Let's start the next section, Lenz law. Okay, see, coming to Lenz law class, Lenz law basically says that, see, let's say I have a coil over here. Okay, now because of change in magnetic field, there will be a change in magnetic flux. Okay, change in magnetic field to change in magnetic flux. Now see, because of this change in flux, what happens? There is an induced current present in the circuit. Induced current means the one which is not from the battery, from the circuit. The one which is present, this induced current is the one which is present due to the change in the magnetic field. Okay, induced EMF or induced current. Now the Lenz law says that this induced current present in the circuit will oppose the cause that produces it. What are their causes? It will oppose the cause. It will set its direction in such a manner that it will oppose its cause. That is what is Lenz law, and it is in accordance with the conservation of energy. Okay, so direction of induced current is such that it opposes the cause that produces it, that is change in flux. Like, see, it is because of this, so it will oppose it. Like, I'll show you. Let's say we have a coil, okay, and there's a bar magnet, north pole, south pole, it is approaching. Now, class, what will happen? See, when the bar magnet will come closer, magnetic field lines will increase. Okay. When the magnetic field lines will increase, what will happen? The flux will increase. You are just concerned with the change, whether there's a change in the magnetic flux or not, or magnetic field or not. Just change. Don't focus on increase or decrease. Just focus on the change. So yes, increase is a change. Yes, a change is there. So this will produce the induced EMF and the induced current. Now we have to set up its direction. What induced current will do? It will try to oppose its cause. What was the cause? Increasing magnetic field. How can the increased magnetic field be decreased? By repelling the bar magnet. If this is thrown away, then the magnetic field will decrease. So this coil will develop a north polarity. North-north will repel itself, the bar magnet will go away. So this is the north polarity. This is how I told you in magnetic moment, put an N. So what's the direction of the induced current in this? Direction will be anti-clockwise. Cause is approaching north pole. Aim is to oppose the north pole. So what? How can it be solved? By developing north polarity so that it can be repelled. Is this example clear? She Halima? Okay. Let's say if I change this, let's say this is the coil and I have a bar magnet. South pole is approaching. Now see what will happen. Again, even if the south pole is approaching, magnetic field will be developed. It will increase, flux will increase, induced current will be there, induced EMF will be there. Okay. Now, Oishi, you tell me what should be the direction of the induced current? What should be the polarity of the coil? Oishi?
South to north.
Polarity of this coil facing the bar magnet, south or north?
It should be south. No,
It
no,
should
north,
be
north.
no, south. See, south will only repel, no? It what
Yeah.
induced current will try to do? Its aim is to decrease the magnetic field. How can it be decreased? By repelling it. Okay. One example, let's take this is the coil. This is the bar magnet. This is the north and south, and this is moving away. C class. The magnetic field will decrease because bar magnet is moving away. Flux will further decrease. Okay. Induced current will be there and induced EMF will be there. Now, Halima, you tell me what will be the direction of the means what will be the polarity of the coil?
It is to attract the North Pole, right? So it will be south.
Very good. The aim will be to oppose. Now this is decreasing. So aim is to increase. Correct. How can it be increased? By developing south polarity. Very good. Is this part clear to both of you? Lenz law?
Yes, ma'am.
Okay. Write it one more example from NCERT I'll discuss and then this topic is done. This will also be over. Please write it.
Done, ma'am. Done, ma'am.
Okay, see, the question which I was saying from NCRT. Look, just be attentive and answer one thing. Let's say I have a coil and this coil is coming inside. Halima, answer few things. Just tell me, Halima, that will the magnetic field increase or decrease in this case? Halima, when the coil is entering, do you think the magnetic field will increase or decrease?
Increase.
Increase, very good. Magnetic field will increase and the magnetic flux will also increase. Now, induced current will try to do what? Increase the magnetic field or decrease?
Decrease.
Decrease, very good. Now, see, aim is to decrease the magnetic field. There is original magnetic field which is inside. Now, induced magnetic field has two options. It can be put either inside or it can be put outside. These are the two options. Now, you said, Halima, that magnetic field has to be decreased. So, which one do you think is preferable, outwards or inwards? Has to decrease the magnetic field.
Inwards.
See, inwards will be added up. Further magnetic
So,
field will increase.
both
Okay?
words.
Opposite, yes. So, what you do, magnetic field is outwards. Put your thumb out. Now, see, where are your fingers pointing? Means where are your fingers getting curled? Clockwise or anti-clockwise, Halima? When you put your thumb out in the direction of induced,
Clockwise.
clockwise. If you put your right hand thumb clockwise, check. Where are the fingers getting curled? Thumb out.
Anti-clockwise.
Anti-clockwise, okay? Like this. So, direction is anti-clockwise. Very good. Oishi, you tell me if this is the coil, this is coming out. What do you think magnetic field will increase or decrease, Oishi? Oishi, you
It
there?
will,
Yeah.
yeah,
Huh.
it will decrease. It's
It
coming
will
out.
decrease. Yes, because it is coming out. Flux will also decrease. Now, what will be the aim of this induced current according to Lenz's law?
To increase the magnetic field.
To increase. Now, original magnetic field is inside. So, where should the induced be? Induced
Outside.
should outside. See, now outside and inside will make
It's
one.
already outside, no?
No, it's inside. Cross symbol is for inwards, no?
Okay. Okay.
You have to pick between these two. See, if you choose this one, first one, it will be like this. Induced and outside. This will be subtracted. We want to increase it, no? We'll choose it in the
So
same
in
direction.
the same direction.
Same direction, that is inwards. Both will be inwards. Now, Oishi, put your right thumb inside. See where are the fingers curling.
In clockwise direction.
Clockwise direction. Very good. So direction is clockwise. Clear? Both of you, both the paths. Oishi and Halima.
Mm.
Okay. The explanation is written. One I have marked, and two for the green ones together, red ones together. Just write it. That completes with Lenz's law too. Now one class is just needed. Induction is left, and motional EMF I'll complete it right now only.
Ma'am,
Yeah.
your magnetic field is going out of the field. We need to add a bit.
Where?
The magnetic field. The direction should be equal or opposite.
Where exactly?
Ma'am, if the coil is entering.
Huh? This one, second one.
Yeah, ma'am.
Okay, then.
Then the magnetic field should be opposite or equal.
They should be opposite, no? Because the magnetic field has to be decreased according to the Lenz's law. So, original magnetic field is inwards. Induced will be outwards. Right?
Yeah.
So, original will be inwards. Induced will be outwards. So, they'll be subtracted. So, less magnetic field will be there. Okay?
Okay.
Okay, write it. Then let's just quickly discuss Lenz's law also. Sorry, emotional EMF.
But into the paper, B will always increase, and out of the paper, it will decrease.
It's not about inwards increasing or outwards decreasing. In the question, the magnetic field is given inwards, right? So now you will check. If you want to increase the magnetic field, like if the induced current wants to increase the magnetic field, you will put it in the same direction, whether it's inwards or outwards. Like if the same person had the magnetic field outwards, you would have taken outwards as our common direction. We are taking and considering them as vectors, no? So your main purpose is that you're solving vectors. Two vectors in opposite direction will be subtracted, two vectors in the same direction will be added. Okay?
So how does the question come? Like, how do the questions come
A
out?
question will have everything written, like where is the magnetic field associated. Like in this question, the figure is made. So it will ask you the a coil of area this or ABCD coil is entering the magnetic field. Tell the direction of the induced current like this. It will be mentioned. You will not have vague
Okay,
information
so
because
when it's
yeah.
entering the magnetic field,
Huh?
like the causes B is increasing, and we have to decrease it.
What?
Like when the magnetic field is into the paper, then we
Huh?
have to decrease the magnetic field, right?
That's what I'm saying, Vashi. This is not a thing to remember. In this particular question, the magnetic field is inside, and you want to decrease the magnetic field here. So you have
Okay,
taken
I
your
get it.
okay. In this
Yeah.
particular case, it is. If this was given outwards, everything would have changed. You keep in mind that you're dealing with vectors. This will increase and opposite will decrease. Okay.
Yeah.
See, class motional EMF basically means that when the conductor is moving, so potential is known as motional EMF. See, motion means movement, right? EMF means the voltage. Like if I say, let's say I have made 13, this is like a track, and I have a conductor. Okay, over it, if I have a conductor, this is the conductor. This has certain velocity. It is moving with some velocity. Let's say this is moving with some velocity v. Okay. Length of the conductor is, let's say, L, and this variable distance is x, which is getting varied. So this conductor is slidable over this and movable over this. So this conductor, the potential in this conductor will be known as motional EMF. So from the term, it's a very easy topic class. EMF induced across the ends of a conductor due to its motion in a magnetic field is called motional EMF. That's it. Means conductor which is in motion, motional EMF. Usually we have static values. Now C class. Magnetic flux is equal to B into area. Area of this rectangular loop will be L into X. Length into breadth, L into X. Put it here. So flux will be B L into X. Now induced EMF is minus d phi over dt. Put it here, minus of d BLX over dt. Take out the constant terms, minus BL dx over dt. Can anyone tell me what is dx over dt? Huh?
B velocity.
Velocity. Very good. So finally, you will get the motional EMF formula as minus BLV. Minus again is due to Lenz's law, we know. So you can simply write it as BLV. This is what your motional EMF is. Numerical, I'll discuss later. First, tell me, till here is it clear? Halima and Oishi?
Yes, ma'am.
Okay, then write down this also. Now, just a small topic. Induction is left. Induction has two parts, self and mutual. Then we'll start with alternating current. That would be the last chapter for you, Halima. Oishi, since, no, with which chapter did you start, Oishi? Directly ray optics, no?
Yes, ma'am.
Okay, so EM waves will be left for you. Okay, fine.
Done, ma'am.
Okay, Lima Ishi, you can leave. We'll continue from here in the next class. One class is required. That will complete this chapter. Okay. Thank you.